Hi everybody. My name is Nicolae Muntean. I am a professor at the Politehnica University of Timișoara, Romania. My skills and those of the team I belong to are in power electronics systems. The presentation we will make are from the field of DC-DC converters in the hybrid structures, which we have studied in recent years. In order to be well understood, I will use an English language correction software in my presentation, so my voice might sound a bit artificial. Let's start.
We have chosen to present to you some of the achievements of our team in the field of DC converters, more precisely, on some configurations that we have developed in recent years, called in the literature DC hybrid converters. Part of these configurations were proposed by Axelrod, Berkovich, and Ioannovici in several articles, starting with 2004. Our team developed these configurations, studied them in detail, theoretically and experimentally, proposing at the same time potential applications. Our presentations are divided into several chapters. The first part, which I will present to you in the following, refers to generalities regarding this category of converters, how they are built, basic schemes, a brief analytical description and main waveforms. The following chapters will address several structures in detail, including sizing, stability, numerical simulation and experimental results in concrete applications of these converters. The presentations that will follow will be made by the members of our team who dealt in detail with these aspects, published articles in the field and developed PhD theses. The equipment with power electronics, in the current sense, represents the set of static converters arranged between two active sources or between the source and the load, which has the role of controlling the flow of electromagnetic energy at the parameters imposed by the process, under the conditions required by the yield and reliability. DC converters represent a class of equipment with power electronics, which has registered a particularly positive dynamic in recent years, supported mainly by the renewable energy industries, DC electricity distribution, automotive, telecommunications, lighting, IT and aerospace. Based on the pulse width modulation principle, DCs are interposed between the DC source and load, or between two DC sources. Depending on the ratio of input to output voltages, DC can be buck or boost. Inserting switched cells into classical type structures, DC converters achieve an increased ratio, compared to classical configurations, between the terminal voltages. These configurations were named hybrid DC-DC converters. In this slide, step-down type cells are presented, made with switched capacitors, respectively switched inductances. In Figure A, the two identical capacitors C1 and C2 are charged in series and discharged in parallel, thus obtaining a halving of the voltage applied to the cell terminals. In Figures B and C, the two identical inductances are connected in series and then parallel, thus achieving a doubling of the generated current. The states of the circuits for the time intervals in a switching period are shown here. It can be observed the series parallel arrangement of the reactive elements of the circuits. Step-up switched cells are shown in this slide, also made with switched capacitors, respectively switched inductances cells. In figures A and B, the two equal capacitors are charged in parallel and discharged in series, doubling the voltage across the cell. In figure C, two identical inductances are connected in parallel and then in series with the same effect. The states of the circuits for the time intervals in a switching period are shown here. It can be observed the series parallel arrangement of the reactive elements of the circuits. This table presents a synthesis of the integration possibilities of the previously described cells, in different classical converter configurations and the ratios between the output and input voltages. It can be observed that in all cases higher voltage ratios are obtained than converters made in classic structures. Let's see some examples of connecting switched cells in classic converter structures. We will start with one-quadrant converters, with unidirectional power flow. The first structure presented is the hybrid converter with switched capacitors. This is the circuit diagram. It can be seen that the switched capacitor cell is connected to the input of a buck-type converter. This is the buck converter basic circuit, and this is the switched capacitor cell connected at the converter input. The circuit configurations for the time intervals of a switching period are presented in this slide. We can see that during T-off time the capacitors are connected in series, and during T-on time the capacitors are connected in parallel, so that the voltage at the input of the buck converter is halved. The voltage conversion ratio between the output and the input voltages is given by the relation presented in this slide. It can be seen that the ratio is 2-D higher, compared with a classical buck converter. These are the simulation and experimental results of the voltage across the switching cell. It can be seen that the voltage varies in the range of 50% T-on to 100% T-off of the input converter voltage. The experimental model is presented in this slide. You can see the input inductance and the switched capacitor cell. For a more complete comparison between this hybrid converter and the classical buck converter is presented in these tables. The analysis was made in the continuous current conduction mode. You can see the stress of the power transistor and the peak input current comparisons. A second example of a one-quadrant DC hybrid converter is the one with switched inductances cell. This is the circuit diagram. It can be seen that the switched inductor cell is connected at the output of a buck-type converter. This is the buck converter basic circuit, and this is the switched inductive cell connected at the converter output. The circuit configurations for the time intervals of a switching period are presented in this slide. We can see that during T-on time the inductors are connected in series, and during T-off time the inductors are connected in parallel, so that the output current is doubled. The voltage conversion ratio between the output and the input voltages is given by the same relation. It can be seen that the ratio is also 2-D higher, compared with a classical buck converter. These are the simulation and experimental results of the current waveform across the switching cell. It can be seen that the current varies in the range of 100% T-on to 200% T-off of the output converter current. For a more complete comparison between this hybrid converter and the classical buck converter is presented in these tables. The analysis was made in the continuous current conduction mode. You can see the stress of the power transistor and the peak input current comparisons. The experimental model is presented in this slide. You can see the two inductances, components of the commutated inductive cell. A third example that we want to present to you is a combination of the first two structures. This results in a hybrid converter with a cell of switched capacitors at the input and a cell of switched inductors at the output, on one side and on the other of a buck converter. This is the circuit diagram. It can be seen that the switched capacitor cell is connected to the input of a buck-type converter, and the inductive cell is connected to the output. The circuit configurations for the time intervals of a switching period are presented in this slide. During T-on switching time interval, the capacitors are connected in parallel and the inductors are connected in series. In the T-off time interval, the capacitors are connected in series, and the inductors are connected in parallel. Thus, the capacitors are charged in series and discharged in parallel, having the input voltage. At the output, the inductors are connected in series and then in parallel, doubling the output current. The voltage conversion ratio between the output and the input voltages is given by the product of the two previously presented converters' voltage ratios. Again, for a more complete comparison between this hybrid converter and the classical buck converter is presented in these tables, including the stress of the power transistor. The analysis was made also in the continuous current conduction mode. A more synthetic comparison between the three structures and the classical buck converter, in terms of voltage conversion ratios, is presented on this slide. It can be seen that the first two structures have identical characteristics, the green and yellow curves. Respectively, the red curve describes the voltage ratio of the third converter. All three variants have clearly superior ratios regarding the voltage conversion factor. Regarding the transistor RMS current, in this slide is presented the values for the previous converters. It can be seen the lower values as a function of the duty cycle for two of the hybrid converter configurations. Regarding the maximum transistor current, the same conclusion can be taken as a result of the equations presented in this slide. Finally, an estimated relative price of the converter's components is shown in this image. The more expensive is the last presented converter due to the larger number of components, including active and passive devices. Multi-input static converters are used to mix multiple power sources onto a single load in a number of applications, renewable energy conversion and smart grids, automotive industry and energy storage systems, telecommunications, IT, etc. The development of this type of converters is based on the introduction into the classic structures of some switched PWM cells, functioning as pulsating sources of voltage or current. Basically, a switched voltage source cell, implemented in buck, cuck and zeta converters, is presented in this slide. On the other hand, current source switched cells with basic implementation in boost, buck boost and SEPIC are shown in this slide. The rules according to which converters with several inputs can be built are series connection of voltage sources, respectively parallel connection of current sources. In this slide is presented dual inputs converters, based on the classical circuits. First is a connection of a 2 buck converters. The second is a connection of buck and buck boost structures. The bellow examples can be extended using capacitive or inductive commutated cells. Voltage switching sources using commutated cells are presented in this slide, for different cells structures. Current switching sources using commutated cells are presented in this slide, also for different cell structures. The 2-input hybrid converter presented in this slide is obtained by integrating a converter with switched inductances cell and one with switched capacities cell, in the same topology, according to the synthesis principles presented previously. A characteristic of this topology, that must be taken into account when evaluating its use in an application, is that only one of the inputs shares common ground with the output. The converter with switched inductances is located in the upper part and is connected to the voltage source V1 through the diode D11, which has the role of blocking the passage of current towards the source. The switched capacitance converter is connected to the voltage source V2, both converters having a resistive load, Rout. Instead of this resistor, a group of batteries can be connected to the output, or a DC bus that provides energy for different DC or AC consumers. As can be seen from this figure, the 2 integrated converters in the 2-input topology do not work independently, because all the power that is taken from the source V2 must pass through the inductances L1 and L3, which are part of the switched inductance converter. However, the control system that generates the control pulses for the 2 transistors must provide independent regulation of the current through each input source. A potential application of dual input converters is in the field of renewable energies, where it is necessary to collect energy from 2 sources of the same or different types. The block diagram of an energy conversion system, in which the converter has the role of collecting energy from a photovoltaic panels, respectively from a wind turbine, which drives a permanent magnet synchronous generator, whose voltage is rectified by a diode bridge, is shown in this figure. The power can be injected into the grid, or feed an inverter for local AC consumers, or be used to charge storage elements. During continuous conduction mode, the converter can be in any one of the 4 operating states, at any given time, determined by the combination of the two control signals of the transistors. These states are listed in this table. The characteristics of the states are as follows. State 1. Transistor T1 is conducting and T2 is blocked. The equivalent circuit is illustrated in this figure. Capacitors C1 and C2 are connected in series via diode D23, and are charged by taking energy from source V2 and inductance L2. The voltage at the terminals of the inductance is negative, which causes the current to decrease. Diodes D21 and D22, respectively D12 and D13, are reverse biased and therefore blocked. The inductances L1 and L3 are connected in series through T1, and the current flowing through the source V1 closes through the forward biased diode D24 and determines the power transfer to the output. The voltage drop across each of the two inductances has a positive or negative sign, depending on the instantaneous relationship between the two voltages. Therefore, the energy in L1 and L3 can rise or fall, and the slope of the current through the inductances can change continuously during operation. If the current slope is positive, part of the energy taken from the source in this state is transferred to the output, and the other part produces the increase of the energy stored in L1 and L3. If the current slope is negative, all the energy taken from V1 and some of the energy stored in L1 and L3 are transferred to the output. Although, theoretically, either of V1 and V2 can be less than V0, because the two-input converter contains two hybrid-type converters, characterized by high conversion ratio. In general, its normal operation requires values for V1 and V2 more greater than VO. State 2. Transistor T1 is blocked and T2 is conducting. This figure shows the equivalent circuit. Capacitors C1 and C2 are connected in parallel through conducting diodes D21 and D22, and inject current into the node connected to the source terminal of transistor T2, which connects the switched capacitor converter to the cell formed by L1, L3, D12 and D13, through which the output power is transferred. The inductances L1 and L3 are connected in parallel through the diodes D12 and D13, and the voltage across each of them can be positive or negative, because the inequality relationship between the output voltage V0 and the voltage Vc can change during operation. Conversely, the voltage on the inductance L2 is always positive, having the effect of increasing the current through it. State 3. Transistors T1 and T2 are conducting. The equivalent circuit is shown in this figure. Inductors L1 and L3 are connected in series through T1, and capacitors C1 and C2 are connected in parallel through D21 and D22 in conduction. The voltage drop across L2, equal to V2 minus Vc in this state, is positive, so the current through L2 and the energy stored in L2 increases. Capacitors C1 and C2 inject current into the node connected to T2, and the energy stored in them decreases. The voltage across each of the inductances L1 and L3 is positive, so the current through the two inductances and the total stored energy increase. It is the only state in which energy is transferred from both sources to the output of the converter. State 4. Transistors T1 and T2 are blocked. This slide shows the equivalent circuit for this state. The inductances L1 and L3 are connected in parallel and part of the energy stored in them is transferred to the output. The voltage across an inductance is negative, minus V0. The current through each is negative sloping under all operating conditions. Inductance L2 supplies the charging current of capacitors C1 and C2, connected in series. The voltage on L2 is always negative, so the current decreases and part of the energy stored in L2 is transferred to the two capacitors. The sequence of states of the converter during operation depends on the relationship that exists between the duty cycles, D1 and D2, of the two transistor PWM control signals. If the same drive frequency is used for both converters, the drive signals of the two transistors can be synchronized on the rising or falling edge, which simplifies the theoretical analysis. In what follows, it is considered that they are synchronized on the rising front, the relationship between the input and output voltages being expressed by the two equations presented here, dependent on the relationship between the duty cycles D1 and D2 of the two transistor PWM control signals. This figure shows, through a three-dimensional graph, the variation of the output voltage for the entire theoretical range of variation of the duty cycles D1 and D2. The input voltages, expressed in per unit, are constant. V1 is equal to 1. V1 being the base voltage for expressing in per unit, and V2 is equal to 1.5. The maximum output voltage is found at the theoretical point with D1 equal to D2 equal to 100%. In this case, the sources V1 and V2 are connected in series through T2, and the output voltage is equal to the sum of the two input voltages, 2.5. If D1 is equal to 100% and D2 is equal to 0, the voltage source V1 is continuously connected to the output through transistor T1, so V0 is 1. If D1 is 0 and D2 is 100%, T2 permanently connects the source of V2 to the output and V1 is completely disconnected. Therefore V0 is 1.5. This picture shows the experimental model of the converter. You can see the modular construction, with the two component converters, connected to each other in the output part. The previous slides presented hybrid step-down converter structures. In the following, some structures of hybrid step-up converters are presented, at the level of basic schemes. The first converter is a boost type with a switched capacitor cell connected to the output. The relationship between the output and input voltages is also presented. It can be seen that at the output a voltage of 1 plus D times higher than in the case of a classic boost converter is obtained. A hybrid boost converter having a cell with switched inductances connected to the input is presented in this slide. It can be observed that a similar relationship is obtained between the two voltages, with that of the previous structure. A hybrid buck-boost converter can be made using the integration of a cell with switched inductances in a classic buck-boost structure. The relationship between the input and output voltages shows us that a double ratio can be obtained, compared to the classic structure. The hybrid DC-DC converters can be implemented also with bidirectional power flow. Microgrids, renewable energy systems, automotive, and other applications often require bidirectional DC-DC converters in order to ensure the power flow between various energy storage elements. Therefore, bidirectional DC-DC converters placed between energy storage devices and DC buses, at different voltage levels, have recently become important research issues. In many cases, the bidirectional converters have to provide a high voltage ratio between input and output. In DC microgrids, the DC-DC bidirectional converters play an important role in the control of the internal DC bus voltage and in maintaining the system power balance. For hybrid energy storage systems, in which both batteries and supercapacitors are used as energy storage devices, two or more bidirectional converters with coordinated control are included. For hybrid energy storage systems, in which both batteries and supercapacitors are used as energy storage devices, two or more bidirectional converters with coordinated control are included. Nowadays, interest in plug-in hybrid electric vehicles imposes the study of new recharge strategies in the energy systems that include renewable energy sources. In this case, a DC distribution bus is easy to be implemented in order to integrate this kind of sources. Furthermore, using bidirectional DC-DC converters in this structure, the energy stored in plug-in hybrid electric vehicles' batteries can be fed back to grid, in the so-called V2G operation. This section presents a bidirectional hybrid switched capacitor converter, which uses a switched capacitive cell in its structure, in order to achieve a wider voltage conversion ratio. The schematic of the converter is developed from the unidirectional hybrid switched capacitor converter, which operates in step-up mode described in a previous section. As presented in this figure, the converter uses transistors in place of the initial diodes, with antiparallel diodes, for bidirectional power flow. As it is the case, positive currents in circuit indicate step-up operation, while negative currents indicate step-down operation. One driving signal is used, which is applied directly to T2 and T3, and inverted for T1. Similar to the one-quadrant converter, the bidirectional structure uses identical capacitors in the switching cell, and the voltage across them is considered equal. During the T-on interval, the two capacitors are connected in parallel through the inductors between the two inputs. The IL1 current indicates the charge or discharge of the switched capacitors, as it is larger than IL2. During the T-off interval, the capacitors are connected in series to the high-voltage side trough, the L2 inductor, and L1 inductor is connected in parallel to the low-voltage side. In step-down operation, the two capacitors are charged in series from the high-voltage input, and are discharged in parallel to the low-voltage side, achieving a voltage halving. The step-up operation is similar to that of the one-quadrant converter, where the capacitors are charged in parallel and discharged in series. A comparison between this structure and other bidirectional converter types is presented in this table, regarding the voltage gain, the switch's stress, and number of components. The simulation and the experimental results presented in this figure confirm the stable operation and a good transition between the two operating modes, from step-up to step-down mode. This slide presents the picture of the experimental model. This section presents a bidirectional hybrid switched inductor converter, which, as the name suggests, uses a switched inductor cell in order to achieve the higher voltage conversion ratio. The schematic of the converter contains 3 transistors, with their respective anti-parallel diodes. The operation is identical to the one-quadrant converter, in the step-down and step-up modes respectively, with the added possibility of using active rectification if MOSFET transistors are used. As a result, only one driving signal is used, applied directly to S1 switch, and inverted for S2 and S3. The 2 equivalent schematics during the T-on and T-off switching interval are presented in this figure. During the T-on interval, the S1 switch is turned on, and the S2 and S3 switches are turned off. Similar to the unidirectional schematics, the 2 inductors and their currents are considered identical for both intervals. During the T-on interval, the 2 inductors are connected in series between the 2 inputs, and the current on the low voltage side is equal to the current through the inductors. The voltage difference between the high voltage VH and the low voltage VL is divided between the 2 inductors. During the T-off interval, the 2 inductors are connected in parallel to VL, and the current on the low voltage side is equal to double the current through the inductors. A detailed comparison between this converter and another bidirectional structure is presented in this table. The inductor's currents and energies, the active components' voltage and current stresses, are presented. Transients from the 2 quadrants operation are presented in this slide. The currents are reversing, proving that the power changes its direction. Finally, for this section, the picture of the experimental model is presented. This presentation reviewed DC converters with a special structure, generically called hybrids, with distinct performances and which the authors have studied and developed in recent years. In the following presentations, hybrid converter configurations will be extensively addressed, theoretically and experimentally, each topology being linked to the industrial application for which it was implemented, so as to give concreteness and justify the approach to the field. The following presentations will introduce details about digital simulations, control and experimental results according to this subject. The objectives of our presentations are related to the opening of collaboration opportunities related to the hybrid DC-DC converters. Thus, we are interested in knowing your opinions and the development of these structures in new configurations and industrial applications. For more information about our research fields, please follow the link. Finally, we would like to thank you for your attention, hoping that the subject is interesting for you, and the next presentations, made by our team members, will stimulate your interest about hybrid DC converters.